Hello everybody, and welcome to this month's meeting of the Sustainability Practice Group.
Thanks, Matt. Today's presentation is a wastewater treatment plant case study on thermal drying to achieve Class A biosolids. Our presenter is Christy M. Schnell, an environmental engineer and senior associate with Gresham Smith & Partners in Nashville. Christy is very experienced in designing wastewater pumping stations, wastewater treatment plants, collection systems, and water treatment plants. She assisted with the design of the canal pumping station in New Orleans following Hurricane Katrina. Additionally, when the city of Nashville experienced historic rainfall and subsequent flooding in Tennessee in 2010, Nashville's Harrington Water Treatment Plant was surrounded and submerged. Christy worked on GSP's team to help Metro Water Services in the city to get this 90 million gallons per day water treatment plant back in operation within 30 days. Christy is a graduate of the University of Louisville with both a bachelor degree and master's of engineering in civil and environmental engineering, as well as a registered professional engineer in Kentucky and Tennessee. Welcome, Christy.
Thank you, Mark. Okay, so as he said, today I'll be talking about the thermal drying to achieve Class A biosolids, a case study in Bowling Green, Kentucky. Hopefully everybody can see my screen. I'd like to recognize some of my co-authors on the project. Ken Baker, also with Gresham Smith, and Scott Neighbors with the City of Bowling Green. Okay, maybe it's going to work. I'm trying to advance the slide.
Just advance one or two clicks.
Did it? Okay.
This is a hidden feature of advance to your next screen, and this is what typically happens with GoToMeeting. It will advance in just a second.
Okay. Maybe.
And this is the part that Matt edits out.
It didn't, yeah, yesterday when we practiced, it didn't go like this.
All right, so are you hitting next or the down key?
Yes, I am trying to. There we go. All right. So it advanced on my screen. Did it advance on yours?
Yes,
okay.
Perfect.
All right. So we're going to start off with a little bit about the project, then get into the Class A technology selection process. I'm going to talk about the RFP process for BGreen's thermal dryer, then have a little bit of a design, construction, operational update, and end with some conclusions. So a little geography to start with. I'm not sure where everybody's situated, but Bowling Green is located in southern Kentucky. It's about an hour north of Nashville or about an hour and a half south of Louisville, Kentucky. Those are the closest major cities. The wastewater treatment plant is situated on the Barren River and collects wastewater from both the city of Bowling Green and parts of Warren County. So here's an aerial of the 10.6 MGD activated biofilter plant. The plant was originally constructed in 1964, and it had this operations building. It had the grid separator, the 3 primary clarifiers, the 2 aeration tanks, these 2 digesters, final clarifiers, and chlorine contact tank. It was then upgraded and renovated in 1973 and became one of the first Neptune microfloc plants in the country. And this utilized 2-stage aerated biotowers with redwood media. And here's one that was still located there before the construction, and the other one sat right there. Now, in addition to these redwood media towers, the upgrade included the additional digester, the additional primary clarifier, 4 final clarifiers, because you had 2 for each of the aerated filters, and then you had your 2 chlorine contact tanks. They converted these to chlorine contact tanks, and you had your post-aeration, and then you had your sludge drying beds. And then in 1992, they upgraded again, and the redwood biomedia filters were replaced with these trickling filter which have plastic media. The wastewater treatment plant was subsequently converted back from, it was a two-stage nitrogenous and carbonaceous treatment. It was just converted back to single-stage treatment. So these two trickling filter towers had these three primary clarifiers that they discharged into, and then they added a solids building where they dewatered their solids with a centrifuge. And they kind of, because they had the trickling filters and they had the additional tankage, the flow comes into the headworks building, and then it goes into the primary clarifiers, and then they had converted these two tanks into aerated sumps, essentially, and then the wastewater was then pumped from those aerated sumps into the two trickling filter towers, and then over to the three primary clarifiers, into the chlorine contact tanks post-aeration, and then it went out to the river. So what was the reason that the plant needed to expand? Well, to start off with, the population growth. There were 17 areas identified in the 201 facilities plan that were expected to experience an average growth rate of 1.45% within the 20-year planning period. So at this growth rate, about 32,000 more people would need treatment services by 2025, which translated to about 7.5 million gallons per day of additional capacity. Also, the existing plant was unable to handle these projected hydraulic loadings. It was determined in the 201 facilities plan that the 10.6 MGD plant was at 75% capacity, which meant that the existing wastewater plant did not have that additional capacity for the population projections. There was the age and condition of the existing infrastructure. As I just mentioned, the last upgrade was in 1992, and so many of the structures had been abandoned during the three upgrades at the plant. There was obsolescence of the existing facility. The existing grit removal system, for example, was inefficient and allowed excessive quantities of grit to pass through and build up in the downstream processes. Additionally, a portion of that influent channel, the influent flow went right through the administration building. So that caused hydrogen sulfide gases to be diffused through the building, which caused significant corrosion problems to the electrical and the electronic equipment. There were also operational and maintenance inefficiencies. One of the biggest operations challenges that they had was dealing with a snail infestation. Bowling Green had been a good neighbor and took a load and ended up with this snail population. And the snails not only affect the biological process by affecting the bacteriological growth in the secondary treatment, but they were also a nuisance because the routine cleaning that was required to remove the accumulated snails. Because since they had those trickling filter towers, the trickling filter media was the ideal habitat for these snails. But then what happened was once they died, they ended up in the pipes and then ended up in those two aeration sumps. And so what the maintenance staff had to do was they had to take those aeration sumps down every 3 months and clean out, basically pump out those dead snail carcasses. And then what they had to do is they took those carcasses, put them in the sludge drying beds. It was a big odor problem, and so just all around, it was just a maintenance nightmare for the guys. And the snails were, unfortunately, asexual, so even if you got rid of all of them, or you thought you got rid of all of them, if one remained, the population would be back within, a few days. There were also minimal monitoring and controls for septic haulers, which resulted in significant quantities of grease to enter the facility unregulated. There were potential nutrient requirements. There were discussions about nutrient requirements being implemented at several Kentucky wastewater treatment plants. The existing plant was not designed to handle these nutrient requirements. Both the 201 facilities plan and the preliminary engineering report verified that the existing plant just did not have the capacity to treat hydraulically or to treat to any of these nutrient requirements that were being proposed. And then the last thing, which is the focus of the talk today, is the long-term sustainable residuals management plan. The only method that they had of disposing of their solids was landfilling. And they landfilled, they had, after it came off the sludge that came off the primary and secondary clarifiers, it was co-settled in the primaries and then pumped over to that dewatering building, and they dewatered with a centrifuge. So then they had to have a truck come in, and they hauled their dewatered solids, which were about 23%, so it's a lot of water that they're hauling, not a lot of solids. They haul their solids one way, 60 miles northeast of the plant. And, you know, that was their only method of disposal. So the managers at BGreen, you know, they said that we need to have a long-term sustainable residuals management plan. So to do this, a project team was formed with project managers, engineers, a biosolids expert, the operations and maintenance staff for BGreen, the BGreen managers, and also the Warren County Water District managers had a little bit of say in the plant expansion, because Warren County Water District decided rather than build a new treatment plant themselves, it was more cost effective to send their waste to BGreen. And so they had a small piece of the say in the puzzle. And then also we included the regulation staff. Now during the process, input from BGMU's operations and maintenance staff was very valuable, and it helped to promote an ownership. Getting their operators buy-in, you know, really helps with, you know, not necessarily just selling the equipment, but, you know, making sure that it was going to be something that worked for their operators and their maintenance staff. So the plant was expanded and upgraded to a 15 MGD sequencing batch reactor, and it was about $40 million in construction costs. Now, in order to keep the existing plant in operation, only 12 MGD of SBR capacity was constructed, which consists of these 4 tanks. Each tank is about 3 million gallons. All the other processes are rated for 15 MGD, though. So what we did to get the wastewater off this administration building, to get rid of those hydrogen sulfide gases, we rerouted the sewers, because they were coming this way. We routed them to this new headworks facility. This new headworks building has fine screening, it has vortex grit removal, and then it's got the influent pumps that pump the wastewater up into the tanks. Now, having that grit removal system, you know, they were having the grit issues before, and having that grit in your downstream process, you know, can really affect your equipment and, you know, the wear on your equipment. So getting that out was, you know, critical. And what they also did with this expansion was they changed their disinfection. They were using chlorine and doing a chlorination dechlorination. They wanted to reduce their risk, so they switched to UV disinfection. And so they've got the UV disinfection over here in their post-aeration structure. And so the waste-activated sludge from the SBRs is pumped over to these 3 sludge holding tanks. Now, these used to be the digesters that had been abandoned in the original construction and the second expansion. They had been abandoned, but they were, you know, structures out there. They were already tanks, so it, you know, reduced capital by using these tanks. They mix using coarse bubble diffusers. They settle and decant in order to achieve about 1 to 1.5% solids. From the sludge holding tanks, it's pumped over to the new dewatering building over here. And the dewatering building, they wanted to keep the centrifuges for dewatering their sludge. Their operators were comfortable with that equipment, so that's what we ended up doing. But at this point in time, you know, they knew that they had this new plant, but they still didn't have that long-term sustainable residuals management plan. So they had to decide whether continuing to landfill their sludge was more cost-effective than going to a Class B or a Class A process. So sludge biosolids, what's the difference? Sludge is essentially residuals before a stabilization process, and it's before the Part 503 criteria have been met, where biosolids are nutrient-rich organic material that results from the treating of the domestic sewage at the wastewater treatment plant. The biosolids have to meet Part 503, and they're essentially a stabilized sludge. And some examples, you can have aerobic digestion, an ATAD process. There's several of them listed there on the screen. So then it was Class B versus Class A. So Class B is less stringent. It contains small but compliant amounts of bacteria, but there are restrictions for crop harvesting, grazing animals, and public content. Where Class A biosolids have minimal levels of pathogens, you can bag or market these biosolids to the public for application on lawns and gardens. These also meet the vector attraction reduction requirements, time and temperature requirements, all of the EPA Part 503 for Class A biosolids. So the team evaluated both the Class A and the Class B processes in an evaluation workshop. We got all of those decision makers in one room and had this workshop. And what we came to, the conclusion was that the investment costs were not significantly greater between Class B and Class A. Biosolids, so the decision was to proceed with the Class A biosolids. Bowling Green is a heavily karst in topography area, so finding a land application site for those Class B solids could be challenging. And there was also a market for the Class A biosolids. Their local farmers were traveling to Louisville and to Nashville to get the Class A products because both Louisville and Nashville produce the Class A biosolids. So they knew there was a market and that they would be in the middle and to, get some of the farmers to come to them, and so they knew that they would have a market for that. So the payback and the long-term sustainability of the Class A biosolids were very promising, and so the decision was to proceed with the Class A. But within the Class A technologies, they did eliminate the digestion. They had previous experience with digestion and just did not want to go down that route again. And also they had some limited capital dollars. Digestion requires a little bit more capital than some of the others. So the next thing that we did was we predicted the plant build-out conditions for the 20-year planning period. We contacted vendors to submit a qualification-based proposal that outlined the costs and requirements for producing that Class A product. The proposals evaluated both capital and life cycle costs, projected labor requirements, equipment required, utility requirements, a description of the end product, and the overall layout or footprint. It was also assumed in the evaluation that the centrifuges would conservatively produce 15 to 18% solids, and that dewatering operations were to be initially 3 days a week with future operations at 5 days a week. And so these initial proposals were received and evaluated in 2008. So the qualification-based RFP evaluated the 3 Class A technologies: thermal drying, alkaline stabilization, and composting. We also kept the no action, the landfill, as a baseline. But within thermal drying, we looked at a couple different dryers. We looked at belt dryers, indirect dryers, microwave dryers, and the direct-fired rotary kiln dryers. So what we ended up doing was we came up with 13 evaluation criteria by the team, that was developed by the team to be used in a qualification-based selection process. And so what we came up with was a screening matrix that formed, so each criteria was assigned a weighting factor of 1 to 5. And then that weighting factor was based on the overall, the importance to BGMU for their residuals management. And so with these weighting factors, then each technology was evaluated on it and was assigned a score of 1 to 5 that was then multiplied by that weighting factor. And so what this matrix did for us was it clearly narrowed down the technologies for the team. And so rather than show you the full matrix, it would take up, it's a big spreadsheet. Here's the results from the screening matrix. The top 5 manufacturers were shortlisted, and were evaluated further. And these 5 encompass 2 out of 3 of the Class A technologies. So we thought, this was a fairly good selection. Composting did score low and was eliminated. This is mainly due to composting requires a very large tract of land. And one of the things I guess I forgot to mention was the site, 45% of the site, the wastewater treatment plant, is in the floodplain. So having the available land to do that composting activity that's not going to be in the floodplain, they just didn't have that. And so composting was eliminated, but we still had the thermal drying, we still had the alkaline stabilization process, and we kept the landfilling option as the baseline. So pros and cons were developed for each manufacturer, and they were taken into consideration along with the cost evaluation. Standard conditions were developed in order to determine the life cycle cost, and all options excluded the cost for dewatering, since it would be the same for every option. We assumed an inflation rate of 4% and that was applied to the utility cost, and a life cycle of 20 years was assumed. These life cycle costs also assumed a beneficial use of the end product. So here you can see all 5 shortlisted Class A processes proved to be more cost-effective than landfilling, which is mainly due to the increase in tipping and transportation fees. And so we could eliminate that landfilling option. The average annual cost per dry ton for the 24-hour day operations ranged from $256 to $314 per dry ton. Now note that the costs presented here are 2008 values, so these would likely be higher if we reevaluated with 2013 dollars due to the increase in fuel. Now, after the initial review in 2008, field trips were scheduled for BGMU personnel. At the end of this field trip period, BGMU had not selected which Class A technology, but they had eliminated the alkaline stabilization. Alkaline stabilization results in a very dusty process, and it has the additional cost for lime, and it requires a large footprint. The end product might not be marketable for Bowling Green because of the karst topography, where the Bowling Green farmers do not need the additional lime in the soil. And Bowling Green had used a similar process previously and had a bad past experience due to it being very odorous and labor intensive. But with the 4 options left, Bowling Green was satisfied that one of the 4 dryers would provide them that long-term sustainable residuals management plan that they were looking for. So the next thing that we did was a specification-based RFP. It was issued in October of 2009 to the 4 shortlisted manufacturers. Now each manufacturer had to list their exceptions that they took to that performance specification. They had to list the greenhouse gas guarantee, which is where each manufacturer was asked to supply a written guarantee that the proposed dryer would comply with EPA's 40 CFR 98 for reporting the greenhouse gases. They also had to provide a life cycle cost analysis based on standard conditions for the utilities. They had to provide the electrical classification requirement, a guaranteed schedule for delivery since time is always of the essence, and a bid bond. Now both of the belt dryer manufacturers decided during the RFP process not to submit due to exceptions that they would have to take in order to meet the performance specifications. So prior to receiving the proposals, evaluation criteria were developed. Proposals were evaluated on both capital and life cycle costs, compliance with the specifications, service facilities, and references. The proposals were opened in November of 2009. And as you can see, the capital and life cycle costs for the 2 dryer manufacturers are shown. Thermal Dryer A had 15% lower capital costs and 2.5% lower life cycle costs and was awarded the contract. Now that 2.5% difference in life cycle cost, based on the big difference in capital costs, was due to Thermal Dryer B had a lower gas usage. So that's how they got to come up in that life cycle cost analysis. But Thermal Dryer A was awarded the contract. Thermal Dryer A was Therma-Flite IC 10,000 indirect dryer. It has the capacity of 10,000 pounds of water removed an hour. And construction began in April 2010, and the dryer facility is now operationally complete. Now, Therma-Flite has been producing screw conveyors in the industrial market since 1939, but they have just recently entered into the municipal market. Therma-Flite's bio screw typically starts here with a feed hopper. This feed hopper has twin intermeshing paddle mixers that keep the biosolids homogenized and breaks up any bridging. Now, due to hydraulic, redundant, and spatial constraints, BGreen's system does not utilize a feed hopper. Instead, they utilize a progressive cavity pump. But either option has to provide a consistent feed rate and material uniformity to the dryer. So the biosolids are then put into the dryer. The biosolids are heated under a slightly negative pressure in a sealed anaerobic environment. Thermal fluid is circulated through these hollow screw rotors and also on the outer jacket of the drying chamber. Then you've got this condenser scrubber that removes the moisture driven off the biosolids, and then biosolids are discharged through this cooling screw. Now, at the time of the evaluation, Therma-Flite only had one municipal installation, and that was in Yakima, Washington. However, it was not operational. So what they decided to do was they had a pilot unit, and they shipped that to Bowling Green, so that way the operators could get their hands dirty. You know, they could see this, even though it was on a small scale, they could operate it, so they knew what they were getting themselves into. The pilot arrived in December of 2008, and overall BGreen personnel were very pleased with the operation and simplicity of the maintenance of this dryer. Now, once the Yakima facility became operational, BGreen took a field trip out to Yakima to see the unit. The unit here in Yakima is an IC 1800 or 1,800 pounds of water removed an hour, which is 4 sizes smaller than the IC 10,000, which was what Bowling Green was going to get. There are currently 5 operational municipal installations that vary in size, but at the time, I think they've come out with a model bigger than Bowling Green's, but at the time of the installation, it was the largest installation Therma-Flite had ever made. And it was also model 001. It was the very first. You know, they had proposed this IC 10,000, but they never made one until Bowling Green. They do, on their website, have an IC 12,000, which would be 12,000 pounds of water removed an hour, and they were looking for some, the city of LA in California was looking to put some of those in, but I'm not sure what the status of that is. So the dryer building was constructed adjacent to the dewatering building. If you remember from the other area, here's the dewatering building. Well, this dryer building was constructed just adjacent to it. And then we have the storage silos here on the right-hand side. The dryer was shipped from Benicia, California to Bowling Green, Kentucky. It arrived in August of 2011. It weighs over 130,000 pounds and had to get special roadway permits since no interstates were taken. The dryer traveled only on secondary highways, which meant that bridges had to be checked to make sure they would support the weight. And while traveling through the Rocky Mountains, the dryer had to travel at about 3 to 4 miles an hour. Commissioning began in June of 2012. So the current operations show that the waste-activated sludge in the sludge holding tanks thickens to about 2.2% solid, which exceeds the design rate. We had designed these holding tanks to thicken to about 1 to 1.5% before being pumped over to the centrifuges. The centrifuges have been consistently dewatering the solids to about 23.5%, which also exceeds the design expectation of 15 to 18% solids. Then from the centrifuges, they drop down into these inclined conveyors, which transport the dewatered cake into the storage hoppers. Here's another picture of the storage hoppers on the left. These wet cake hoppers that we like to call them, they have live bottoms here in the bottom of the wet cake hopper, and they just feed the progressive cavity pumps here in this pit, which is right here. There's the twin screws feeding the progressive cavity pumps. And then the pumps have the option to pump either into the dryer or out to trucks for hauling to the landfill. Now, granted, we wanted to get away from hauling to the landfill, but they don't have N+1. You know, they only bought one dryer. So their backup, if the dryer is down, is to haul to the landfill still. So here's the dryer, and there's the two pipes from the two pumps that go into the dryer and feed the dryer. And here you can see, here's that condenser scrubber, and back here in the background there's your cooling screw where the biosolids discharge. In the room adjacent to the dryer, here's the Fulton thermal fluid heater. It was supplied with the dryer. It heats the thermal fluid to about 535 degrees Fahrenheit. Each hollow screw rotor contains 185 gallons of thermal fluid, and the housing has 300 gallons. The biosolids within the dryer are heated to about 212 degrees Fahrenheit. From the 212 degrees Fahrenheit, that 90% solids is discharged through the cooling screw here. The cooling screw lowers the temperature of the biosolids down to about 112 degrees Fahrenheit. The biosolids are then pneumatically conveyed into these storage silos. Each silo has a carbon monoxide, temperature, and oxygen sensor for monitoring the conditions inside the silos. If a hot spot is detected, the silos can be purged with nitrogen. So here's some data that was collected through April of 2013. The SBRs produce an average of about 16 tons of the 23.5% solids versus the old aerated biofilter plant, which produced about 12.5 tons of 28.5% solids. But however, as most wastewater engineers know, generation of waste-activated sludge from SBRs is going to be significantly more than waste generation from the old coal-settled process. Here's some more data. This is the percent solids data between the two processes. The higher percent solids from the old aerated biofilter plant is due to the primaries. When you have primary sludge with your waste-activated sludge, you get a higher percent solids. We have strictly waste-activated sludge from the SBRs, so that's why the percent solids is a little lower. Now that conservative design value of 15 to 18% solids that we designed the centrifuges around was based on other extended aeration plants using centrifuges for dewatering waste-activated sludge. Unfortunately, the manufacturers, they cannot predict how every sludge is going to produce. But what we did was we contacted other plants that were using waste-activated sludge and dewatering with the centrifuges, and they were saying they typically saw 15 to 18%. Well, Bowling Green can get more than that. So it exceeded our design expectations. Getting that water out up front means that they don't have to necessarily turn the dryer up as high because it's already coming in at a more dewatered rate. And the plant is currently getting the 23.5%. So here's another graph that shows some costs that BGreen paid for landfilling their dewatered sludge. As you can see, there was a spike in May through July of 2012, and that was when the new SBRs were being started up and seeded. They had to end up holding some sludge, and they had to end up hauling some sludge. And so there was also, as you can see, there was a little spike there in February of 2013, and that was when the dryer was out of service. But overall, you could see that declining cost trend, that as BGreen began to dry more solids, they were hauling less solids to the landfill, which was a significant cost savings for Bowling Green. Now the landfill charges, or was currently charging, they did not guarantee these rates for anything more than the year, $100 a load and $32 a ton. Now on average, the SBRs produce about 800 tons of the 23% solids. So that's about $33,000 a month. So that's that red line, that baseline of what they would be paying by not doing anything, by not drying. Just that's what they were going to get. Now by drying, that's about a 4 times reduction, or about 200 tons of solids. Now, yes, running the dryer, they do have an increase in their gas usage that they didn't typically have. That gas is running at about $10,500, that green line. But there's not any hauling costs when you're drying the solids. So that's a savings of about $22,450 a month that Bowling Green is saving by not hauling to the landfill. Now, BGMU has marketed their biosolids as BGreen. They were initially giving it away to local farmers to get their interest, and now that it's proven itself, this year they charged $23 a ton, and they were looking to increase it to $25 a ton next year. Now, on a nutrient-based comparison, the product contains about 5.9% nitrogen, 6.2% phosphorus, and 0% potassium. Now, in comparison, the most commonly used commercial-grade fertilizer is ammonium phosphate, or DAP. It contains 18% nitrogen, 46% phosphorus, and 0% potassium, but it costs $726 a ton. Now, on a nitrogen-to-nitrogen basis, you would need 3 times as much BGreen as you would the DAP to get that same nutrient content. But you're saving $657 a ton because of the difference in cost. You know, Bowling Green's charging $23 a ton and DAP is $726 a ton. Now, if you want to look at it a different way, a full truck of that commercial grade fertilizer, which is about 24 tons, is $17,424. So that same truck of BGreen would be $552, but you need 3 trucks. So that's $1,656 you would have for BGreen versus the $17,424 in DAP. That's a $15,768 savings for the farmers. Now, the farmer that Bowling Green is currently selling their product to is Myers Circle Farm. Now, they did sole source selling to just one local farmer. They're looking to add a second farmer, but this Mr. Myers, he takes all that they have, and he comes about once a week. He lives about 30 miles west of Bowling Green in Elkton, Kentucky, and he was traveling down to Nashville and to Louisville to get, you know, biosolids, or he was paying the price of the fertilizer. Now, he has cattle. He grows about 1,000 acres of corn, 400 acres of wheat, and 600 acres of soybeans. When he was using fertilizer, he didn't use DAP, he used urea, which is another commercial grade fertilizer. It has a higher nitrogen content, but it doesn't have the phosphorus. So in comparison to the DAP that was an 18.46.0, the urea was a 46.00. But after his initial learning period, you know, because he had to learn how much of the BGreen to put on versus how much of the fertilizer he was used to putting on, because of the nitrogen content, you know, he's recognized the value of the biosolids, and he's saving about $456 a ton, and he calls it an excellent investment. At the time when we contacted him, he hadn't brought all of his crops in, but he expected his crop yields to be the same, if not better, than the commercial grade fertilizer. So can thermal drying be an option for medium-sized generators? And the answer is yes. BGMU's story is not unique. Evaluation of a Class A process resulted in an attractive and affordable option for medium-sized generators. What was unique was the involvement and the cooperation of the different utility departments in the decision-making process and all the unique features of the plant. You know, having the very first indirect thermal dryer from Therma-Flite was definitely a big deal for them. So why thermal drying? Long-term disposal options such as landfilling cannot be guaranteed. For one, landfills have finite amount of space. Also, landfills can charge whatever you want, and then you've got the hauling cost. So it wasn't a good option. The current biosolids practice is becoming cost prohibitive, you know, because you've got those tipping and transportation fees. You've got continued regulatory constraints on your Class B land application sites, because you're not getting to that Class A solids, which is safe. You've got an emphasis on green and sustainable solutions. You're taking, a lot of people don't like the term from toilet to tap, but you're taking those solids and you're turning them into a beneficial reuse. You've got continuous feed dryer technology available, so why not use it? You get that volume reduction, you get that water out. You can have biogas utilization, which is also another green sustainable solution if you've got digesters in the mix. And you produce a Class A product. So in conclusion, thermal drying was the right decision for Bowling Green. It provided a long-term sustainable residuals management plan, which is what they were looking for. And this project was recognized by the American Council of Engineering Companies in Tennessee as the 2013 Grand Award winner. They also won the Beneficial Use of Biosolids Award for Kentucky at the Kentucky-Tennessee Water Professionals Conference this past July. There have been articles in Water World and in CE News. And there's another article coming out this month in WENT, in the Water, Environment, and Technology magazine. So as you can see, this project has received and will receive accolades and prove that thermal drying is the right solution. And so with that, I will entertain any questions that you might have.
Hi, Christy. Mark here. With the Therma-Flite not having produced a unit of that size, was that a risk, or was that something your firm already had experience with?
No, it was definitely a risk. It was actually not our recommendation to go, even though they were the lower in capital costs. We were more comfortable going with the other option, which was Comline-Sanderson. Comline-Sanderson was more, was known in the the municipal world. They had, several dryer installations of that size. But the owner, really wanted to go with that innovative technology. It was a risk that they took. Luckily, it's paid off. It was a lot of coordination effort, more on our end as far as the design engineers, because we had to do a little bit more. We couldn't just rely on their experience because they had never conveyed biosolids into storage silos. So, we had to call some other sources and get those biosolids experts to get the right information. But we made it work. But it was definitely a risk, yes.
Matt, did you have questions?
At this point, I don't see any from the audience or any hands raised. So I guess if there's anything else you want to ask Mark, or we'll give it a few minutes. But it seems like Christy did a pretty good job of just describing everything for us.
Yeah, I hope that wasn't too technical for you. I'm sorry.
So the evaluation criteria then, the number of units already in place was not put on the list, because that would have...
Right. It was put on the list. It was one of the... when we did the scores after the second round of proposals came in, Therma-Flite did, that was where they scored low. They scored low on because they only had that one installation and it wasn't operational, where the other manufacturer did have other installations. So they did score low, but the capital costs really, and they knew, Therma-Flite, I think that might have been one of the reasons why their capital was so low, because they wanted to sell that unit.
Well, to prove it could be done, I guess. And
yes, exactly.
But also that $1 million was very persuasive.
Yes.
Did they have to raise money for this, or was this?
They went after some of the green technology money from the government, but they did get a loan from Kentucky Infrastructure Authority, KIA. So they did get a low-interest loan to help pay for that. But what we ended up doing was we rolled, because we knew that they were upgrading their wastewater plant, and we'd been talking to them about the biosolids piece from the beginning, but at the time, they were like, well, we're not sure if we want to do it, and then they ended up, halfway through design and construction, then they wanted to go, proceed forward with the drying. And so it was an additional contract, and it ended up being the same contractor who did both, and so he kind of got to complete both of them concurrently. But they did go after money to help pay for both the wastewater upgrade and the drying piece.
So that green funding was available just to one of the two options?
Yes, right, yeah. And which they could use it for the dryer because that was the green piece. But the SDRs was just the low rate interest one.
And so for the construction, was it Therma-Flite as the contractor, or did they team up with a local builder?
No, the contractor was Judy Construction Company. They're a local, they're out of Lexington, Kentucky.
And so they would have bid either option, or they would have installed either option? They
would have installed either option, yes. And so that's what we ended up doing, is just bidding it out to the general contractor.
So once you knew the equipment costs, then there was additional bidding to find the contractor.
Right, because what Bowling Green was able to do was if they pre-purchased the equipment, they could save on taxes. So the owner actually pre-purchased certain pieces of equipment in the project, and so the contractor just had to put in for the installation cost, and then anything that wasn't that major equipment item, like wasn't the dryer, they had to come up with the cost for the storage silos and the blowers for the pneumatic system and the piping and so forth.
And in the drying, or I guess with more drying, is disposing of the water a problem?
No, because what you end up doing is the water gets discharged, gets cleaned and treated and discharged back to the river.
Okay. Okay.
It goes back into the headworks. Any of the condensate water drains back to the headworks and goes through the treatment process and gets cleaned, goes through the biological process, the UV, post-aeration, then out to the river.
Okay.
It's all
and so that was 2008 and 2010 and 12. How are things going today for them?
They're going pretty good. They had some issues with their odor control unit not performing very well because the odorous air off that scrubber is combined with the odorous air off the wet cake hoppers, and they were seeing high hydrogen sulfide in the odor control unit, and so it just wasn't keeping up, and they were having some complaints from the neighbor when they ran the dryer, because when you run the dryer, it does smell like what you would think it would smell like. And so they have had some issues with the odor control unit, but they've been working those out, and I think they've fixed all of them. They've switched to a carbon type filter. They had a biological filter, and it was just killing the bugs, so they switched to a carbon media filter, and that's worked better for them.
And is your firm taking this approach anywhere else in the country now?
We have. There was talks about some partnerships with Therma-Flite out in California. I'm not sure the status of those because that's a little bit higher up the food chain than me. But I know that there was some talks because there were a couple municipalities out in California that were going to sole source like a design build to Therma-Flite, and then Therma-Flite was going to use our engineering as support services because of the success of the project. But I think a couple of those projects have been put on hold because I haven't heard any news recently about them.
Okay. Matt, if there are no questions, Christy, thank you very much for your presentation. It sounds like this is a process that really should be replicated,
Yes.
both from a green point of view and a cost point of view. So thank you again to all who attended our sustainability practice group. Hope you'll tune in again next month. Thank you very much.
Thank you.